Hello everyone, today we talk about how to make one of our services which is singleton and not scalable. How do we make it that this service is scalable? First of all, let's check how this service works. I talk about the prop management service. If you check currently on GitHub, it is singleton and it can't be run multiple times because every prop management currently is one per map, so you can have one per map. So it kinda scales in this regard, but it's far from perfect. Since I want to teach something, I think it is of great value to make this service scalable, because most likely you will have a similar issue in one of your projects. And while we edit, we will rename it from prop management to enemy management, because it will not only manage props anymore, it will also manage everything attackable basically on the map. And since enemies, in comparison to props, have some artificial intelligence to it, or they move around and they have some more logic, it's not reasonable anymore to have this service singleton. When you just do respawning and maybe tracking some HP and everything, having this service singleton per map is scalable enough, depending on how big your map is and how many props it has, but most likely it will be fine. For our use case, where we want to be as flexible as possible with this service, we might want to make it scalable. And this service has a typical issue when you want to make something scalable. It has the issue that not two services should perform things twice. And there's always this issue which you read often if you do a lot of backend development, which is called at least once, which basically means that your calls can happen more than once. So your calls need to be idempotent, and that's not always easy to do. And we will look into some concepts, what you can do and what we will develop next week together on this service to make it scalable and make it work like we want it to. So let's talk about this service real quick. This service is started once per map, so it doesn't scale pretty well. It will get messages from Redis and will send messages via Redis to our map service. So when a player attacks a prop, then the combat service will send a message to the prop service. It will do the damage to the prop delayed. For example, a player casts a spell and it has a cast time of 2 seconds, then 2 seconds later the prop management will do the damage to the prop. This gives the network enough latency to make the prop damage perfectly on time, so that for the player it looks like there's no delay. So combat service in advance, before the damage will happen, will notify the prop service. Damage will occur. The prop service will apply the damage when it will occur, basically with 0 latency. And then the prop service will update its state in the map service, which will then distribute it to all clients. That's how basically a lot of things work in our backend. The problem is, since we have a config file where each spawner is defined, the prop management basically loads this config file and will manage all the spawners. So if we check the source code of prop management, we will see exactly that. Let's really fast go over it. So when the prop service starts, it will eventually go into initialize, and initialize will load the config and will process any spawner, and then it will register to when a skill is casted on the map. And when a skill is casted on the map, like I said before, it will check if it manages the prop, and if that's the case, it will add the damage to a queue. The queue is updated every now and then. There should be an update function or something here. The queue is updated, and when the queue is basically the time is to do damage, then on damage is called, and then damage to the prop is done. And if the prop has less than 0 or 0 HP, it will die, and it will give loot and everything. It will send some messages around to notify other things that loot has happened. It will notify that the player has done damage, which will trigger the damage number, and it will update its state on the map service. This is all fine and great, and it works, but we want to make this service scalable. The problem, first of all, or one of the solution that might come into your mind quite easily, we have multiple spawners. We could make one spawner, one service responsible for one spawner, or one service responsible for one category of props and everything like that. That's a good idea. It will work, and it will definitely make the service better scalable, and it's very good controllable. It doesn't cost pretty much much more than what we do before, so cost wise it doesn't expand, which is a very important factor when you have a low budget project. If you have a AAA project, maybe budget doesn't bother you too much, but even though in a large scale everything gets expensive, so in my opinion, you should really put emphasis in cost and how much everything will cost at the end, because something that might cost you in your dev environment 1 or 2 euros might cost you a couple 100k in a production environment, just because it needs to be scaled that big. So we definitely look into the cost a lot here. It's actually quite easy to implement. We could give every service basically on startup a category, and then it will just manage the categories it is assigned to, which is really easy to do. It's very cost effective. But the learning effect behind that when I develop it like that is pretty much none. And I want to blow this design up a little bit to show a little bit more concepts and to make it even better scalable and more dynamically. The problem with this approach is, let's say we don't have that much players in the weekend from Monday to Friday. We just need more services than one on the weekend. Then it might be more feasible to have it downscaled in the week, and in the weekend we upscale it. And that's not possible with this approach, because the amount of spawners will definitely define how much services there are, and that might be fine, but maybe we will find a solution that even is able to downscale back to one service if that is what we do. Because let's say we have round about 10 to 20 spawner categories per map, and we have 20 maps, then we have 400 services, which is quite a lot for a small project. 400 services which basically sleep all the time just because they have nothing to do. Then it would be great to scale them down to one per map, or maybe you have maps that are more demanding, and then you will scale just those maps up. That would be great. And also, the backend structure is defined by game design, and this is something which I don't like, because then your game designer needs to understand how your backend works and vice versa, and that's not a good idea to have, in my opinion. For me, this is a one-man project. I'm game designer and backend dev, so for me that would be obviously fine. but I think in bigger projects it would be great if backend developers and game designers basically game designers have to tell the backend developers what they want to have, but not the other way around. And another problem is that you always want to look into is when one of those services died. So since we're using Kubernetes and Kubernetes will restart the service, this isn't too much of a deal, but still there will be downtime. So let's say our services in a very demanding environment where CPUs are starving already needs 1 or 2 minutes to boot up. Let's say one of those services fails, then it takes 1 or 2 minutes for this service to be available again, and this is very bad. It's better than having nothing, and it's still better than our singleton, because when in our singleton, when it's go down, it would take this 1 or 2 minutes for any prop or enemy to be able to take damage again. And for the other approach, it will be just one category, so you might be lucky. Still, it would be great if we can improve on that. So another idea which I really like, which is often done in scalable backend projects, is to have the state in a database. I put Cosmos DB because we are using Cosmos DB as a database currently. And your services are basically stateless, which means you can just increase how many you have and decrease them, and they have no idea what spawner or anything is related to them. They just take those events. For example, player attacked prop A. They will take this event, will trigger the timer, and after the timer will occur, they will write in the database damage has occurred. The reason why you need the database is basically to have a single point of truth. So when another service takes over, let's say player A attacks prop A and this service takes over the damage dealing, and player B also attacks prop A and this service does the damage, then they will both update the state in the database, and eventually the database will hold the true state, and the map service could also get the data from the database or something like that. That's possible, that's often done. For example, this is a typical REST service web API thing where you have a database behind the scene and you have a barrage of services which basically just take the request, update or check the database and answer back. For example, our login in our game exactly works like that, or the character service also works like that. They are pretty much brain dead. They just get the request, do the database stuff they need to do, and maybe put some messages into Redis and response back to the client. That's exactly how they work, and this basically scales endlessly. I can remove and add services how much I want, and it still works. This is very easy to implement because we already have implemented this. It will be seamless on failure, so when one fails, then basically the requests that go into the service would most likely be a Redis queue in our case, and the queue entry is locked and only removed after execution. So when a service fails while it's processing a queue entry, the entry is not processed and another service will take over. This is definitely at least once, so we have to make it as idempotent as possible. Idempotent basically means if you execute the function multiple times, the end result is the same. Let's really first make one example. Let's say you have an HP property and that is 100, and your service call on damage basically does HP minus minus. This is not idempotent because it will change depending on how often I call the onDamage function. If I call it once, then HP will be 99, and if I call it twice, HP will be 98. If I do a call like that and make it new HP equals 99, then it's idempotent. How many times I call it, HP at the end will always be 99. So to make it more, to give it more sense, let's say we have a damage done function and it will minus equal damage done. If you call this 2 times, then this will end into 99 and then 98 after the second call, which is not what we want because the second call basically is a false call. And if we do it like that, new HP and new HP will be the value, then no matter how often a false call comes in, it will be fine. And if a second player will actually attack, then we need to obviously make it like that. This is the problem with at least once, and a lot of clients of mine very much underestimate this issue. It doesn't happen too often if your backend is not starving for memory, CPU or anything and isn't hitting any limits. Most likely you won't feel this issue, but in this case I can really good explain how this issue will happen. Let's say we have a Redis queue entry that says do 1 damage to this prop, and the service, our top service, will execute this. And it writes it to the database, and while it's writing to the database, it will crash. Or I will scale down while it's writing to the database. Doesn't need to be a faulty crash, could be me scaling down the service. I don't want 3, I just want 2 anymore, because like I said, I need 3 in the weekend, but in the week I just need 2, so I shut 1 down, and my code doesn't gracefully shut it down, which can happen. And then it's writing to the database, and before it removes the entry from the queue, it will shut down, or it will crash, or anything will happen. Things will happen in your backend. And maybe we are unlucky and it has already updated the entry in the database. Since these things are 2 different databases, we don't have any transaction or kind of shenanigans we could normally do when we just do Redis. We could update the state and remove the queue entry in a transaction, and only if this transaction is committed, Redis will update is basically as an atomic operation. This will be fine, you won't have any issues with that. But since this is not the case here, it will be at least once execution. And the queue entry is not deleted, the service is shutting down, but the HP is already removed at the Cosmos DB. What will happen, another one will take over and will execute it again, and then our function got called twice. This is how this happens. Honestly, for enemies and props and everything, this is not an issue. No player will complain if they do double damage. It's not perfect, but it will work. It's a good solution. The only thing why I don't want to use it is because I think Cosmos DB is not a cheap service. It's an awesome, great service, but it's not cheap. And I don't want to spend that much money on infrastructure and the service. I could also leverage Redis as the database for that, which would be way cheaper, and we could do transaction, which makes a lot of these issues go away. But I decided against it because this wouldn't be educational. We wouldn't explore a new architecture which we haven't before. And this is what I want to do. Else I emphasize that it's a great design too, because we don't need to save the enemy HP and everything very persistent. It would be fine if the backend restarts, all enemies respawn with full health. We could scrape the Cosmos DB and use Redis as basically data store also. to hold the state, then this would be a very good design. There's nothing to talk against it. Cost will be low. We will pay for the Redis anyway, and everything would work. There's just a small issue who handles respawns and things like that. So who initialize triggers that the enemies will respawn and everything, but that's handleable. That's no problem. We even could make one singleton service which just triggers respawning, which isn't too much of a deal. So what we will do, we will have one service which kinda is singleton, which manages the other services. So we have this one service I called load balancer here, which basically knows the configuration and knows every spawner, and we have some workers, and those workers will be pretty much stateless. They just cache their own enemies which they manage, and we will develop it when new workers will come or workers will leave. The load balancer will balance the load accordingly, so it will rebalance for new and moving services enemies around. Let's say we have in 6 props, prop 1 to 6, and the load balancer has 3 workers, then eventually it will assign two props to each worker. That's how this will work. So we don't want the load balancer to be singleton, but this is basically a singleton task. What we can do, and this is basically the new thing that we will implement, we will implement something like a primary secondary model, which if you are into databases, you basically know this, where databases primary and secondaries both listen to changes, but only the primary is basically applying the changes to the data. But when the primary crashes, a secondary directly can take over. So we don't have to wait for Kubernetes to spawn the primary again. A secondary will take over, will be the new primary, which can happen very fast in seconds. And then after Kubernetes has started the primary again, it will become a secondary. That's basically how this works. So if primary crashes, secondary will take over, and if primary boots up again, it will be a secondary. So we have always a backup if something goes wrong. Since the load balancing work is not hard to compute and doesn't need to be scalable too much, we could even combine those strategies. For example, we could make a load balancer for each spawner or category, so we can make the scale even further, but I don't think that it's needed for now. What I really want to do is want to implement and show the primary secondary model. So we have no seamless failure, which basically means if one of the worker crashes, their state will be lost. This can be fixed if we put the state into the Redis. But if we do that, then we could basically implement something like this. Then we might do it in the future just to make it work really, really well. What I mean with failed seamlessly is, for let's say this service handles prop A, and if this service crashes and I don't write the state back to the Redis, and a new service takes over prop A, it will basically respawn the prop. So it will handle the prop like it has never existed before. And so for the player, it looks like a prop will despawn and it will respawn in another place with full HP, which might not be the best case, but like I said, we could also save the state into Redis, and if another one takes over, it reads it from Redis, and then it feels for the player like nothing has changed. Maybe we will implement that. I don't want to promise it, but we will try it definitely. Contribution on distribution is low, so the load balancer computational task is not too big, so it's okay when we have just one instance of the service, but we will have multiple secondaries to take over if one crashes. So we are failure resistance, more failure resistance like this for sure. And if computation on the enemy or prop worker gets high because we implement AI, enemies walking around attacking back and everything, we can scale this part. So the AI and everything is scalable by the workers, and the load balancing basically doesn't need to be scaled too much. We have to keep in mind that you have one load balancer per map, so it's still scalable with the maps. Smaller maps basically scale better than bigger maps. There are also ways to, like I said, to scale the load balancer, like with the category thing. Then you have per map, per category, and so this also scales pretty well. But I think for the first iteration we implemented as one load balancer per map. And we need to implement the primary secondary logic, which basically is a negative side for implementation and a real project, where we could do this one, and we have Redis and Cosmos DB basically are services which are fully implemented, and we just need to implement those services. But for learning purposes, I think it's a really good idea to implement primary and secondary logic, just to show you how it could be done. And it will leverage a feature from Redis. A lot of databases have this feature, but we will basically leverage our Redis here. And Redis has a feature which basically will write an entry into our cache or database only when it not exists. And what we will do when a load balancer service boots up, let's say we have 3 of them, and they boot up, they are all secondaries. And all of them try to write into Redis, I am the primary. So let's say we have a field primary, and they will write their own ID. They will on boot up generate a UID that is unique, and that's their own ID. And they try to write primary to their own ID only if it not exists. What Redis will do, 2 of them will get an exception, and 1 of them will actually go through and write the value. And after they read the value back from Redis, they will know if they are the primary or not. So they on boot up, they all try to push into Redis, I'm the primary. Just 1 wins, and this at the end is the primary. And their whole logic or writing logic is done only by the primary, and secondaries are just listening and consuming the state as it comes by. And if the primary dies, they will take over. And how does that work? Basically, every service, primary and secondary, will write a heartbeat to Redis. They basically just write their current date when they last executed their loop to Redis. And then every secondary will check, is the primary still responding with his heartbeat in time? So let's say we write the heartbeat every second, and then every secondary will check, maybe is it 3 or roughly 3 seconds away that the primary has answered. If that's not the case, if the primary hasn't answered in 2 or 3 iterations where it should have written a heartbeat to Redis, then we will remove the primary from its role. And this basically just works removing this entry in Redis, the primary entry with the UID. It will remove it, and even the primary, if it's not crashed, let's say it has some severe lag, it will read back from Redis, okay, I'm not the primary again anymore, someone else will take over. And if that's the case, the race starts again, everyone tries to write primary its own UID, and if that's the case, we have a new primary, which could result in the old primary again being the primary. But most likely it will happen that the primary actually have crashed or something, and then the secondaries will remove him from its primary role and one of the other secondaries will take over. One problem with that is, which could happen if your code really crashes, that the secondary will take over, will become the new primary and will directly crash again. And then another secondary will take over, will become the primary and crashes again. But none of these other architectures is protected against this issue. So we could have a cascading failure when a secondary takes over, but this would be a catastrophic failure in every of those architectures. That's basically not handleable. But still, it's still very good to have this. The reason for that is a friend of mine just asked me, why are you doing this? When the primary crashes, Kubernetes will restart the primary anyway. That's only maybe takes a long time, and B, let's say the primary doesn't crash, but on the same node the primary is running, a lot of other computational stuff is basically taking up the resources, or a lot of resources, and the primary is not the best idea. And this will result in a heartbeat getting very late into Redis and one of the secondaries taking over. So this also rebalances our secondaries where it can run smoothly. So it's actually not a bad design in my opinion. And it will solve a lot of issues, but it will also make everything more work for us to implement. Another, I didn't invent this structure. I've worked with a service from Microsoft which is called Service Fabric, and every Service Fabric service has this primary secondary feature when they are stateful. And we basically try to implement a easier version of that, which might be not as robust as the Service Fabric one, but it will be robust enough for us. So basically the logic will be, we send heartbeat, and if I'm the primary, I will do my primary stuff. If I'm not the primary, I will do my secondary stuff that I explained. So we have multiple cases. When we have no primary, everyone writes their ID to the primary, one wins the race and other loses to optimistic concurrency and will stay the primary, like I said before. Now let's say a secondary failure. So a secondary fails, no one cares. So if a secondary fails, primary is still fine, no one cares. But if a primary fails, secondary will check there's no primaries anymore that is responding. Let's remove the primary and the race starts again. And one of the two will win the race and will become the new primary. That's what we will implement next week, and we will basically implement our props like they are currently, but with this architecture behind it. And then we will basically make calls for our props to have some AI, so they can walk around and do computational stuff which takes a lot of CPU resources, which will make our old structure not work anymore, but the new architecture will be fine. So let's say we will spawn over 1000 props in our map, then I think this structure will basically not work anymore feasible. And even if we have to go to 10,000, we will test that in next week, where we will put this architecture basically fully to its limit, where it will not work anymore more properly, and then we will show that this architecture here still works super fine. And that's, sadly, this is just a concept video. I didn't have the time to implement that now, but I will implement it next week with you together. This is everything I have for this week. I want to thank my Patreon Julian from the bottom of my heart for supporting this project. This is it. Have a good week. Bye.